In this video, we're going to continue doing integration by substitution. And like I said in the other one, this is not enough practice. You really need to do a lot of these to get better, like so many that you can handle without going crazy. That's the only way you'll get good at substitution. Okay, so let's do our first example. We're going to integrate each of the following. We're dealing with definite integrals in this example. And again, one of these can be done without substitution, one of them with substitution. And hopefully you can see the difference. The one that has the constant is the one that does not need substitution. Usually when you have x's in the numerator and the denominator, that's usually when you need to do something different using substitution is the only thing you're going to learn in this course. So let's do that first one. That's an inverse trig function. And usually inverse trig functions have squares at the bottom, two squares being added or subtracted, and in this case it's a square root. So you can rewrite that as a squared minus u squared. A would be 3 in this case, u would be x, and that's actually the inverse sign, straightforward, no bells or whistles on this one. It's just direct inverse sign integration. So you can rewrite our formula or our integrand as 3 squared minus x squared in the bottom and just straight plug into the formula. And then this is when you have an indefinite, you have to remember to add the c, but we have definite integral this time. So from 0 to 3, that means that we're going to integrate, plug in a 3, plug in a 0, and subtract them, and then simplify this. We end up with the inverse sign of 1 and the inverse sign of 0. If you remember what you're finding with inverse sign, the answer is the angle in which the sign is 1 and the sign is 0, but it has to be within the domain of negative pi over 2 to pi over 2. So the sign is 1 here because that's where the y coordinate on the unit circle is 1. So this is pi over 2 on this one. And the sign is 0 here because that's where the y coordinate is 0 on the unit circle. So we end up with pi over 2 minus 0, or just straight pi over 2 for the answer to this one. That one's pretty straightforward. No substitution needed. It was an inverse trig function. Be careful with those. Those are sneaky. So make sure you become familiar. Make them your best friend. The next one does need substitution though, because we have that extra x in the numerator. So a lot of times with substitution, you need to use like a denominator or an exponent or underneath the radical as your u. So this one is probably going to be 9 minus x squared as your u. This is kind of guess and check at first when you're learning how, just to play around with it and make sure everything fits. So the derivative of u with respect to x is negative 2x, and we can multiply by dx. We want to get the dx over there with the x. And now this is where you start looking at what you have and if you can make everything fit. So for example, you can actually rewrite this integral as 1 over 9 minus x squared times x dx. Because that x is really in the numerator. If you want to do this, you can put it like this and multiply top times top, bottom times bottom, and it still works out. Now I did that because the 9 minus x squared in the radical at the bottom is now the square root of u. And that's great because now that's nice and pretty. You're going to be able to write that as a power soon. So we have to work on this piece and get rid of that, replace it with something else, and we have that right here. We just need to get rid of that negative 2, and because it's a constant, you're allowed to move it over to the other side and make it look like 1/2 du, or du over negative 2, however you want to write it. And now that takes care of this. And we have everything we need replaced. There's nothing extra. There's nothing missing. So we are good to go. We can take this, take our integral, rewrite it. So now it looks like this. So before we move on though, let's talk about the limits of integration, because this 3 and this 0, they apply to the x's, not to the u's. So we need to deal with that. If you're going to substitute and replace those x's with u's, you need to replace the limits of integration to match the u's as well. So you start out with your u situation that you created over here, and all you do is plug in. Take this and plug it in for x. When x equals 0, u is going to equal 9. So you would really just put a 9 here instead of a 0. And you do the same thing with the 3. When x equals 3, u is going to equal 0. So instead of a 3 up here, it's actually a 9. So now you have two new limits of integration that match your u's. And that allows you to do the definite integral without having to go back to revert it back to the x's, which is more complicated. We're simplifying the way it looks, so keep it with the u's, but just always remember to change your limits of integration to match the u's. Okay, so I'm just going to rewrite this. Put that negative 1/2 out front. And now my integrand is 1 over the square root of u du. Very good. This is beautiful because we can integrate that. Now, I don't know if you were thinking this already, but these are out of order. That 9 should really be on top. The bigger number is on top, the smaller number is on the bottom. Remember, it's A and B, and A is the smaller number. So when this happens, it's okay. All you have to do is switch them around and make the entire integral negative or opposite. So I would multiply the negative 1 in front of the integral. And by doing that, it actually turns this negative 1/2 into a positive 1/2. So I'm allowed to switch these around. It's now 0 on the bottom, which is where it's supposed to be. But as long as you remember to multiply the front of the integral by negative 1, you're allowed to swap them and multiply by negative 1. So now that's why this is a positive 1/2 here. Okay, so now we're good to go to integrate. Even though it's a quotient, it's all good because we can bring that to the numerator. That's really a power. It's the square root of x, or the square root of u, whatever, is 1/2 power. Put it in the numerator, it's negative 1/2. So now you can use the power rule, which is where you have the exponent plus 1 and then divide by that number. So we're going to have a negative 1/2 plus 1. We're going to have to make that 2 halves. So this will become positive 1/2, and then we're going to have to divide by 1/2. And remember, when you divide by a fraction, you're really just multiplying by the reciprocal. So it's, instead of dividing by 1/2, it's like multiplying by 2 over 1. And we can factor that 2 over 1 out and multiply it to the 1/2 on the outside, and it cancels that the 2 and the 1/2 are gone. You're just left with the square root of u, which is u to the 1/2 power. And now the fundamental theorem happens. Plug in the 9, plug in the 0, subtract them. Final answer is 3 here. Okay, I have one more for you. Let's integrate this crazy looking thing. Now, first of all, we cannot integrate this for 2 reasons, like the way it looks. Number 1 reason is it's a product. We have 1 plus x, the quantity, times that e function. The product right there means we're not allowed to integrate. But even if that 1 plus x wasn't there, what if it was just the e function? We would not be able to integrate this either. That or that. We're only allowed to integrate this. And that equals itself, actually. So we need to get it in the form of e to the power of 1, like e to this. It's going to be a u in our case. That's what we're looking for. So let's see. You want to just look for the innermost piece. That's usually a good way to find u. You start that way. So let's say u is 1 plus x. So now do the derivative. The derivative of u with respect to x. The derivative of 1 is 0. The derivative of x is just 1. So you have the derivative of u equals, here I skipped this step. You don't really have to write it if you remember to put the dx on the other side. So now let's look at our integral. We have, this is going to be u. So that's gone. It's a u. We actually have a u here too. So now it's times e to the u squared power. And then this dx is actually du now. So great, we replaced everything, but we still can't integrate that because number one, it's a product, still a product. Number two, even if it wasn't a product, we wouldn't be able to integrate this piece because of that u squared. It has to just be a u, no exponent, no stuff. So this is no good. So how about we try something else for u? Instead of it being 1 plus x, how about we make it this whole exponent here? Make it 1 plus x all squared. So now remember the derivative. This is stuff. You have to use the chain rule here. So we're going to need to take the power rule, put the 2 out front, and then that's all now to the first power, and then times the derivative of the inside. 2 times whatever's here to the first power times the derivative of whatever's inside. So in this case, it'll just be 1 again, 1 dx. So our derivative, 2 times 1 plus x times dx. So let's take a look at our integral again. We can maybe make this work. I'm going to rewrite the integral so that this part is first. I'm allowed to do that because the multiplication here, it's all good. Multiplication, you're allowed to rearrange it. And now notice, this piece is now my u. This is u, so I'm going to have e to the u power, and that's a great thing. And then if I can just replace 1 plus x dx with this expression somehow, I'm good to go. And you can. Notice we have 1 plus x dx right here. We just need to divide by 2. And you can make it du over 2 if you like that better than the 1/2. I personally like the fraction instead of du over 2. But either way, this is now going to be 1/2 du, and we'll be able to factor that out. And then we'll be left with this. And that's very integratable. So let me do that in writing here instead of my handwriting. So we divided everything by 2 over here. We go back to the integral. We're going to rearrange it. And you don't have to rearrange it, but it does help you see it a little better. That this piece right here is going to be what we substitute for the 1/2 du. And this piece right here is going to be our u. So we're good. E to the u times 1/2 du. Pull that 1/2 out. And now you can integrate e to the u power. It's itself. So nice. E is the easiest one to remember because it is itself. And this is an indefinite integral. So we have to remember to plus c. So we have 1/2 e to the u power plus c. But because this is an indefinite one, like the last one we did had those limits of integration and we replaced them using the u, but we don't have that this time. So let's go back to x. Let's put our final answer back in x form. And remember that u was 1 plus x to the second power. And that's it. All good. Hopefully that helps a little. Please practice.